Welcome to this Friday's class. We're going to finish up talking about the test and start looking at Chapter 4 in preparation for next week. So with that, I'm going to jump directly to the Word document. Everyone should have received a copy of the test. Everyone can now access it, but maybe you want to wait till we finish review just to make sure we've covered all the things. So, okay, we had last left off. That's fine, that's fine. We had last left off. That one right there is empirical formula one. We turned grams to moles and then find the simplest whole number ratio. That one turned out to be C1H2O1, I think. Okay. All right, chemical formula. Be able to either turn formula to name or name to formula. Both of those are fair game for the exam. If it's name, so like this one, we have to look at what we have here. We have to look at where does this get classified under. This one right here, SO4 is sulfate. SO4 is sulfate. So when we add a bunch of hydrogens to sulfate, it becomes an acid. So this becomes 8, gets turned into ic acid. So this would be sulfuric acid. Sulfuric acid. Now this one, this is a metal and a non-metal. So iron oxide, but iron happens to be a transition metal. It's not zinc, it's not silver, it's not aluminum, so it's not one of the always one state. It could be two possible states, sometimes more. So we have to classify this one. Specifically, we look to oxygen to give us our hint. Oxygen is group 6, meaning it takes 2 elements to the right to make it 8. So oxygen is 2 minus. If oxygen is 2 minus, iron must be 2 plus. So as we write the name, we want to specifically say iron 2 oxide, not just iron oxide, but iron 2 oxide. Now, if you leave off the parentheses, I'll go back and give you credit for it, but it might mark you wrong initially if you do that. But as long as you're indicating 2 some way or another, I'll be able to give you credit. 12. 12, perfectly legit, perfectly reasonable. What is the mass percent of zinc in zinc carbonate? There's a lot of people who made stupid mistakes on the lab 2, figuring out what mass percent. Mass percent is always the mass of the element or compound you care about over the total mass of the mixture or total mass of the compound. You're only looking at the important aspects, not like the beaker it's in or anything like that. So in this case, we want the mass percent. I'm going to go to board work. The mass percent. Oh, geez, it jumped all the way to the top. Sorry, I know what's doing that. It's my fault for doing the fast. Mass percent. Yeah, there we go. Mass percent. The mass percent is going to be the percent is going to be the mass of zinc over the mass of zinc carbonate times 100. So we have to find out what is the molar mass of zinc, and then what is the molar mass of zinc carbonate. To do this, we go to our periodic table. Just because the test is online, just because I include the periodic table in the test, doesn't mean you can't have another copy in front of you. For goodness sakes, otherwise you're going to have to be scrolling to the top every time you need to look up a element, and that could be really annoying. So zinc, I happen to have an idea of what its mass is because I did this like yesterday. Zinc is like 65.3 grams per mole. Now zinc carbonate. So we're going to take that 65.3. We're going to add on carbon, which is 12. We're going to add on 3 oxygens, each at 16, which is going to be what? 48. And if you're like, wow, he knows his like crazy math, it's like you do 16 times 3 like a billion times and you're bound to remember it. 48 plus 12 is 60. So you get 125.3 grams per mole. Now, as I said, I may be zooming through this at lightning speed. I don't expect you to do that. I give you like 2 hours for the test. So use your resources within reason. 65.3 divided by 125.3. Have a calculator. You don't have to do everything mental math. It's just, I'm doing this to save a little bit of time. You do that and you multiply by 100 and you'd get what percentage is zinc. Zinc is 52.1%. 52.1. Moving back to, okay. We're skipping 13. 13 is a different chapter. 14 is a different chapter. 15, we could probably do it, but different chapter. So 16, 17, and 20, I think, are the last ones we can do that are legitimate problem. The problems that relate to our chapter. 16 is just a different version of the lead problem. The lead problem was, if I have this many molecules, how much will it weigh? This one in particular is, if we have this many grams, how many molecules will be present? So first, we're going to write out our 23.1 grams cobalt chloride. Oh, yeah. Oh, God. That's stupid. Okay, I'm just trying to... there we are. Okay. So the next thing we need to do is... find what is the molar mass of cobalt and chloride. Cobalt is 58.9. Cobalt is 58.9. Chlorine, 35.45. And there's 2 of them. So that puts me at 70.9. 70.9 and 58.9 add up to give you 129.8. 129.8 grams per mole. Now, here's where dimensional analysis helps us. Dimensional analysis states that if we want to get to molecules, we need to go through moles. If we want to get through to moles, we have to cancel out our grams. So I set this up 129.8 grams in 1 mole. Grams and grams cancel. And this number will give us how many moles of cobalt chloride we have. The next we should do is turn this into molecules. To do that, we have to cancel out moles. Avogadro's number says there is 6.02 times 10 to the 23rd molecules in 1 mole. 1 mole, 1 mole. So now we have our function set up. Everything on top gets multiplied. Everything on bottom gets divided. And what do we have? What's the answer? Only one of these answers, I mean, there may be a couple answers that seem reasonable, but one of these is going to be way better than the other. So 129.8. And then times 6.02. So going back to our setup, I got, and take a minute, try to figure out, but I got 1.07 times 10 to the 23rd, or answer D. You could have got C if you had multiplied by 129. No, you might have been. Yeah, you probably could have got C if you multiplied by 129. I mean, there's various ways to get the other ones if you screw up here and there. But a big number, a small number divided by a small number multiplied by a big number gives us D. Now, set number 17. What is the name of this? Now, silver is a transition metal. Chloride is a nonmetal. So no matter what, it's going to be named like an ionic compound. So that leaves C and D as incorrect right off the bat. You should recognize silver is not a nonmetal, so it can't be named like a bimolecular. And the second element is never going to be INE. It's always going to be IDE or IC or 8. So we have silver chloride or silver 1 chloride. Now here's where this one is tricky. Silver is one of the 2 to 3 exceptions that I asked you to learn, that silver is only ever +1. And because silver is only ever +1, we don't need to emphasize its +1-edness. And so it actually is only A, silver chloride. It is the one exception. I may not hit those exceptions hard on the test, but those exceptions are still there. Okay, the last one we'll do. If iron makes up 69.9% of iron 3 oxide, how much iron could be recovered from a 293 gram sample? You don't even need the molecular formula here to do this. You don't even need the molecular formula here to, oh, for God's sake. It's fine. Okay. So this is just a rearrangement of the mass percent. Instead of finding out the percent by dividing 2 masses, we're going to take a percent and take a mass to find what is the theoretical yield. How much iron could we get out of this iron ore? So if it's percent mass iron over mass Fe2O3, which is the iron oxide, times 100. We don't actually care what the formula is, but that's the formula. Well, normally we would have these two numbers and we would be finding the mass percent, but now we're working backwards. 69.9 equals mass iron over 293 grams of iron oxide times 100. So we're trying to find the mass of iron. Now, if you can set up that equation, hopefully mathematically you're in good shape. Hopefully you can solve this. Because what do we get? What do we have to do to get that by itself? Step 1, divide by 100 to both sides. That puts that at 0.699 equals mass iron over 293 grams. Next step, you multiply both sides by 293. And you're left with mass of iron equals, what, like 205 grams. Answer B. Though taking a quick look at that, really answer B is the only one that makes any sense if you understand what this question is asking. If 70% of the mass is iron, and it's like 300. What's 70% of 300? It's going to be a reasonable size number. It's a good chunk. Answer A, 419, means you've got more iron than you started with. You somehow opened a carton of a dozen eggs, and there's 20 eggs in that carton of a dozen. How did you get more eggs than could possibly fit? How did you get more iron than we started with? Mass came out of nowhere. So that one's right out. And these two are both so small to be fractions of 1% of the mass. Like 1%, maybe 2% of the mass. It'd be like far, far less than that. So the only one that even is semi-reasonable in this case is B. But once again, you still could get those answers if you set this problem up incorrectly. Divided when you should have multiplied. Or multiplied when you should have divided. So please be wary. I am tricksy that way. Let me go ahead and close this down. How are we doing on time? So that was the stuff relevant to us. That is that was the test material that's relevant to us. I will go ahead and post a crib for both of those in the Google Classroom. Not that we need it, but it's going to be there. Work on that and post that. But let's go ahead and continue with the PowerPoint. Save. Just a second. Okay. I know this meme's getting a little old. I haven't quite updated it since I first put it up there, but it's still very relevant. We are going to start by looking at light. How light, especially how light can act as both a wave and then as a particle. It's both either or. It is one and the other at the same time. And we'll look eventually how atoms and electrons will actually act as waves and particles. The first thing we're going to do is talk about light, and that's what the majority of next week's lab will be over. So one thing at a time. I'd ideally like to get to the point where we can do the only math of the chapter, which is not too bad as far as math goes. None of this stuff will be on this test, though. The first thing we need to note is that the big thing we're talking about is actually electromagnetic radiation. It is a type of energy, a type of energy that light is but one simple part. Electromagnetic radiation can be absorbed by objects. It can be emitted by objects. We all know objects can absorb light. They can also emit light. If you've ever had those stars you put up on the ceiling, the glow-in-the-dark stars, they're emitting light after they absorb the light of your room. So all EM radiation can travel through pure vacuum. This is different from sound waves. Sound waves, another type of energy, need particles to transfer. That's why the old trope is, in space, no one can hear you scream, because in a pure vacuum, the sound waves can't transfer. But then again, Star Wars wouldn't be very fun if we actually paid attention to science and didn't allow those nice explosions and whooshing sounds. So I'm not going to Neil deGrasse Tyson and shit all over everyone's parade and say, oh, we got to ruin Star Wars now. Now, this is an important part. All EM radiation has a maximum speed. That speed is in vacuum, and that speed is defined as the constant c, being 2.998 times 10 to the 8th meters per second. Oftentimes just abbreviated as 3 times 10 to the 8th meters per second. But that is the speed of light, often referred to as speed of light. But this is the speed of all electromagnetic radiation, all of them. Now, electromagnetic radiation can speed up, well, it can slow down. Sorry, it can't really speed up from that, but it can always slow down when it reaches various mediums. Like light in our atmosphere is going slightly slower than that. Light, when it hits water, will go even slower. Light, as it passes through a prism or other opaque solids, will go even slower. But it's still going wicked fast. You're not going to be able to really notice it too much. But as we picture this electromagnetic radiation, we often think of it as a wave undulating back and forth, like the waves of the ocean. You see the crests and the valleys as they come in a continuous motion at us. Now, if you talk to the physics professor, there's 3 ways to really look at these. Amplitude is one of them, but we will not worry about amplitude at all. So the 2 ways we are going to describe waves is with wavelength and frequency. The first thing is wavelength, which is literally as it sounds, the length between waves. It's the measurement of one part of the wave to where it exactly repeats. How long is this wave? Hill to hill, trough to trough, middle to middle. It should be the same throughout. It's a continuous wave at a constant wavelength. When we try to measure this, it's going to be in a distance. Like, could be meters, could be kilometers, could be centimeters, could be micrometers, nanometers, fractions of nanometers. All of these are valid units. It's just a distance. And when we look at this, the way we represent wavelength is with the Greek letter lambda, which looks like an upside down Y. The Greek letter lambda. Now, where there's wavelength, there must also be frequency. Now, if wavelength is how wide are these waves, frequency would be how fast do they repeat? How fast are they passing through in a given time? Just like in the ocean, even long waves aren't nearly as bad if you have a long gap before the next wave hits you. But if you're being hit with hundreds of little small waves, it can really knock you off your feet. So the same way is, so we're looking up that picture in the top right. If this is an image of, say, 1 second of time of a wavelength passing through, the guy with the long wavelength has like 1, 2, 3, 4, 5, 6 waves that are passing through during this snapshot in time. If we look at the shorter one, I think what I calculated last time was like 10 or 11, maybe 10 and a half, something like that wavelengths passing through. So frequency is the rate at which a wave would be passing through. It is defined by the Greek letter nu, and in this Microsoft Word set, just looks like a V. But really, it looks like a wavy V, kind of like it's either a wave itself, or maybe it has an emo haircut covering its eye, or it's a kind of funky looking V, but the Greek letter nu. Now the units of wavelength, frequency, are inverse seconds. Inverse seconds, which means seconds to the negative first power, also gone as 1/2 or per second. The idea being that you're talking about how many waves are passing per second. But another way, an inverse second is also equal to 1 hertz. One inverse second is equal to 1 hertz. And you may recognize the term hertz. If you've ever looked at the electronic information on, say, a speaker, on a stereo, it's going to give you some of the frequency in hertz, which tells you how fast can these sound waves come out of the speaker. How many sound waves can come out in a given time. And they're measuring that. And so obviously the higher frequency, the more complex the sounds that can be produced. But either way, there is a constant relationship between the two. Given that this is the first major equation we need to learn for this chapter. C equals lambda nu. C equals lambda nu. We're essentially saying the speed of light in a vacuum, which is constant, is equal to the frequency times the wavelength, meaning as frequency goes up, more waves pass by, but the waves get shorter. If the waves get longer, then we have less waves passing through in that same bit of time. So as you see, these long wavelengths have less waves. These short wavelengths have more waves. That relationship right there is always constant inverse relationship. One gets greater, the other gets smaller. If you notice, if wavelength is in a unit of distance and frequency is a per second, when you combine them together, what do you get? You get a velocity, or the speed of light. So if frequency is in meters, frequency is per second and wavelength is in meters, meters combined with per second to get you meters per second. So we got to watch out for our units there. But looking at the whole EM spectrum, there's a very, very wide range. Light is but a tiny, tiny range on there. What we actually see with our eyes is actually just a small fraction. The 400 nanometer to 700 nanometer region covers the whole Roy G. Biv. But that's all we can see. But there's a whole lot out there that isn't there. If we take it further, so beyond violet is ultraviolet, that the light from our sun that burns our skin. We can further separate that into like UVA, UVB, UVC based on the frequency of those sunlight particles. Going past UV, ultraviolet, we get into the X-rays, getting stronger. You know, all that stuff we produce in the doctor's office moves at the speed of light. It's being produced there. And then gamma rays. Gamma rays. If you know anything about Marvel Comics, you can remember, like, well, Incredible Hulk. What supposedly happened to him? He got hit by a bunch of gamma rays. You know anything about, like, Fantastic Four? They went into space, got hit by a bunch of gamma rays. But in more reality, it's one of those things scientists have to protect. Astronauts spend too much time in space, they're going to get a high dosage of gamma rays, which is going to hurt their DNA. We have to have a way to prevent that. Normally, our atmosphere absorbs most of that and protects us, keeps us from dying horribly. Now, going the other way, from red, we have infrared. You know, our basic thermal imaging. All that uses infrared light to help image all of our heat motion. Going below that, we have microwaves. So all of our microwave ovens are producing EM radiation that causes things to heat up. And then, of course, radio and TV waves. As we move from left to right, we see the frequency is going up on the left and down on the right, and the wavelength is going way, way up. These radio and TV waves could be hundreds of kilometers wide. So really long waves. And it's moving down, maybe we're in the centimeters to millimeters range. And then we're going into millimeters to like micrometers and nanometers. And then we're going sub-nanometers when we get all the way over here. So we're talking about a very wide range here. In fact, while that shows us our visible range, different animals have different eyesight visible ranges. I think cats can see a little bit into ultraviolet. A lot of bees and butterflies and other bugs can see well into the ultraviolet. And in fact, plants have some beautiful ultraviolet colors that we can't see that help attract insects, pollinators to them. So there's lots of things going on that we can't quite observe. Remember, all of these guys are traveling at the speed of light. So even though we're worried about light going from how long it takes the light from the sun to reach us, all that television we are producing, sent into space, speed of light traveling to all the other planets. We can send radio waves, try to communicate with outer space, but it's still traveling at the speed of light. One thing to note, and we'll see this in a few other slides, the higher the frequency, the greater the energy, which is why we need to protect ourselves from UV rays, X-rays, and gamma rays. They're bad for you because they have a very high frequency. Radio waves, TV waves, they're so ubiquitous, but they're so low energy that they don't really affect us, that we don't have to worry about them. Otherwise, we would have been well and truly screwed a long time ago. But the first thing we're going to really talk about is, and the first thing we're really going to look in lab is about the atomic spectra. If we shine a beam of white light on a prism, so that white light, that light just from our light bulbs overhead, that light from the sun, we shine it on the prism, a prism will diffract it into a rainbow, the Roy G. Biv rainbow. That whole rainbow is called a continuous spectrum. But all those colors together are actually, when you snap them into one, make up that white light. We just perceive all the colors together as white light. Now, what's causing that to be split? Well, as we said, light travels at different rates in different mediums. So as it hits a prism or some other diffracting gradient, it's going to cause these guys to bend as they slow down. And certain wavelengths of light are going to bend more than others. So we create a greater bend, and thus they separate from one another as one light beam splits into thousands of tiny little wavelengths that we perceive. That happens when this is why we see rainbows, because we have water droplets in the air that are bending light. This is why our atmosphere bends this during sunset, which is why it turns our normally blue sky into red because of how the light is hitting it. So the spectrum is produced by a separate, yeah. Now, the various colors in our fabrics. I see a red shirt, for example. That's the colors of our shirts are being produced by the absorption and reflection of other colors of light. If we look at, this is entirely different from the paint wheel. Rather than the color spectrum of painting, this is the color spectrum of our light. We can draw a wheel of the Roy G. Biv. Red, orange, yellow, blue, green, blue, violet. Green, blue, violet. Every color that we perceive is caused by the absorption of the opposite color and the reflection of the others. So a red shirt would absorb chiefly green light. And so what we're seeing is the absence of green makes that red really pop. If I saw a blue shirt, it would be absorbing mostly orange colored light. So chlorophyll on the plants would be absorbing mostly low energy red. Carotene and beta carotene on what makes carrots orange are absorbing mostly high energy blue light. That's not to say they don't absorb some of the others to some extent, but they absorb mainly the opposite color, which is why we see that color so intensely. Now, these colors we can see can also be seen via light emission rather than reflection. So when a compound gets energized, it will release energy. It could do it as heat, but it often does this as light. In the case of, say, fireworks. So we burn some metals, they're going to produce different colors because they're going to release that energy somewhere. They have to do that in the form of light energy. So, now, if we electrically excite tubes filled with gases, we will get various colors depending on what the gas is. Just like the cathode ray tube, where it was mostly a vacuum, we got the electrons to pass through and we had a current. Well, now, if we have a gas of all just one gas and we do the same thing, we electrically excite it, the gas will start to glow. And depending on the gas, we're going to get a different glow. The neon lights that we used to be famous for, not as big of a thing nowadays, were tubes of neon gas that emit that nice orange light. The street lamps we see have sodium vapor. That's why we have that dull yellow at nighttime of the street lamps. But we can also get yellow from helium. You can get, if you electronically excite hydrogen, we get a nice red light. Carbon dioxide can give you white. Mercury vapors can give you blue. Each gas will emit a different colored light, and we'll play around with these guys in lab. But if we diffract this light that is given off, we'll get several distinct wavelengths that will actually depend on the element. If you can see down here, hydrogen gives off like a violet, a blue, a green, and a red. And all those come together. When we combine them as one, we get the red light that we see. The mercury gets a violet, like a blue, greenish yellow, then a bunch in the yellow and the orange, and then maybe one in the red. All those are going to combine together to give us what are blue. Sodium down there is going to have some greens, a whole bunch of yellows. Some of these similar to mercury, but not quite the same. Some oranges, some reds, and all those are going to combine together to give us our yellow. Now, as I said, these distinct wavelengths depend on the element. Because these are lines given off when we excite the atom, we call this an emission spectrum because it's emitting this light under electrical excitement. But because it gives us specific lines and not a continuous spectrum, we also call it a line spectrum. Now, this is how they used to determine whether you created a new element. This is how they used to. Each element has its own unique line spectrum. And if you record where exactly these lines are, you can say, oh, is this a new element or is it a different element? They would burn this, excite this, collect the line spectrum and say, does this match any of our database of anything new? And like, oh, no, that iron, that's just a new form of iron ore. It's nothing that we haven't already seen. But this idea is actually how we discovered helium. We took the atomic spectra of the sun, and we saw, oh yeah, there's hydrogen in there, which is what we expected. But we also saw a line spectra from an element that we did not recognize. And we said, oh, the sun must be made up of a new element that we don't quite understand. The reason why helium has its name is because of the Greek word helios. Helios was the god of the sun. Helios, a Greek word for that. And so we have helium coming from there. Of course, we later found helium on Earth, but we first discovered it, noble gas not really reacting, because we saw it in the sun. So we will be able to observe these line spectra in lab because we will have prismatic glasses that we can wear. Now, so we're going to talk about all this is all to do with the wavelengths of light. So most of the time, light will act like a wave, but in certain specific effects, it will act like a particle, like something concrete, discrete, not just a constantly moving object, but something we can hold in our hands, something we can measure. For example, if you shoot a monochromatic laser onto a metal, so you shoot, say, a red laser onto a metal, sometimes electrons will be emitted. Say I shoot a red laser, say I shoot a green laser, say I shoot a blue laser onto a metal. Occasionally, electrons will be emitted. The kinetic energy of those electrons will depend both on the metal, but they'll also depend on the wavelength of light. If I change the intensity of light, that will only increase the amount of electrons. So if I shoot red light at, like, say, aluminum, maybe nothing happens. If I shoot green light at aluminum, suddenly it shoots off electrical sparks that electrons I can measure. If I increase the intensity of the green laser, so I have like 5 green lasers pointing at it, or like a really, really strong green laser, I don't get faster electrons, I only get more electrons. But if I up it to a blue laser, which would be stronger, I would get faster electrons shooting off of it. Now, this is actually what Albert Einstein got his first Nobel Prize for this, explaining the photoelectric effect. That light is in fact acting like tiny packets of energy called photons. And when these packets of energy strike the metal, they will transfer that energy, causing the electrons to be ejected. So the idea is, if I hit the metal with enough energy, I can shake the electrons free. If I have low energy, nothing happens. It's like red rover. If I'm moving too slow, I get absorbed, nothing happens. But if I'm moving fast enough, I strike hard enough, I break through, maybe I'm going to shake off someone who gets lost. So here's the second equation that we'll need to know. Energy of light is related to the frequency. So the energy is equal to h Nu. Remember, nu is our frequency. H is known as Planck's constant. It's a really, really small number, 6.626 times 10 to the negative 34th joule seconds. The units are there so that the frequencies per second cancels out with the seconds. So you would get an answer as an energy in joules. So this is a really small number. But then again, we're talking about individual photons here. Individual photons. One photon is like talking about individual atoms. Don't worry about memorizing Planck's constant. I will always give it to you. I will always give it to you because it's, I may know it, but you guys, it's one of those weird things out there. Now, each metal will have a specific minimum energy required to eject a photoelectron called the work function phi, which is just h nu. And the basic idea is that if light has enough energy, the electron will be ejected. Any excess gets converted into kinetic energy. So the kinetic energy is the energy of light minus the work function phi. So kinetic energy is equal to h nu minus phi, which is a constant. So if I need 500 joules to kick off an electron and I produce 700 joules of energy, I'm going to convert those electrons into 200 kilojoules of kinetic energy. But so this is the math, some of the math you'll have to do for the pre-lab. If you read the lab report carefully, it will show you this math and how to do it. But I'm going to go ahead and do these examples, and that's where we're going to finish up. I know I'm running a little long, but I want to be able to have shown you at least one example before the pre-lab so you won't be scrambling on Wednesday. Because of Labor Day, I won't see you again till Wednesday. So the first one, what is the frequency of yellow light? Something of 580 nanometers wavelength. So how do we do that? The frequency, C equals lambda nu. So if C is 2.998 times 10 to the 8th meters per second, and I want frequency in per seconds, I got to take C divided by lambda equals nu. Now here's the hard part. I have to turn nanometers into meters. I have to turn nanometers into meters. This is where you can really screw up. Nanometers is small. Nanometers is small. So 580 nanometers, there is 10 to the 9th nanometers in 1 meter. This conversion means I have 5.8 times 10 to the negative 7th meters. Really small number. Really small number. So back to here, C divided by lambda. If you screw up your conversion, you're going to get a number that's 10 to the 18th off in the wrong direction. So 2.998 times 10 to the 8th divided by 5.8 times 10 to the negative 7th. Doing that, you would get 5.17, I'll just say 5.17 times 10 to the 14th. 5.17 times 10 to the 14th per seconds. That's a big number, but that's okay. Got to remember, these numbers are okay to be really, really big. Because what is the energy of that yellow light? What is the energy of that yellow light? Well, the next equation, energy is equal to h Nu. Nu is 6.626 times 10 to the negative 34th. So 6.626 times 10 to the negative 34th joule seconds times our 5.17 times 10 to the 14th per seconds is going to give us a really small number, because even though 10 to the 14th is big, 10 to the negative 34th is small. So you do that, you would get the energy of one particle of yellow light is 3.43 times 10 to the negative 19th joules. Now, finally, if the kinetic energy of a photoelectron emitted, if the metal has a work function of 1.52. That last one is just, we're going to take 3.42. Oh, I said 3.43. And subtract 1.52. Both of these are 10 to the negative 19th. So 1.91 times 10 to the negative 19th. But so question A, question B will be on the pre-lab. Question A and question B will be on the pre-lab. So just be prepared. Okay, that's where we're going to stop. Don't forget the test is due by Monday, but you don't have to do it anytime before then. You have 2 hours. Take your time. Make sure you do it right. Have a good day.